So most recently, we've been talking about our half-angle formulas and using our half-angle formulas to help us in evaluating trig functions. Well, here's an example where we're going to use a half-angle formula to help us in solving an equation. This particular problem says find all the solutions of the equation in the interval 0 to 2 pi. Here we have the cosine of x over 2 minus the sine of x is equal to 0. Now notice that I have two different trig functions and the quantity inside of each trig function is different. Here I have an x over 2 and here I have an x. If both of these were an x over 2, I might be able to use a simple u substitution. But because these two quantities are different, we need to use our half-angle formula for cosine. Cosine u over 2 is equal to plus or minus the square root of 1 plus the cosine of u divided by 2. Now again, we have to use a half-angle formula because that's going to make the quantity inside of my trig function for cosine here the same as what we have for sine. So utilizing that formula, I get plus or minus the square root of 1 plus cosine x divided by 2 minus the sine of x is equal to 0. Notice that we have to keep this plus or minus in front because if we're finding solutions in the interval 0 to 2 pi, well, those angles could be in any of the four quadrants. So we must include the plus or minus in the equation. Well, that makes this equation pretty ugly. So what can we do to help us get rid of this square root? Squaring both sides of the equation is going to help. Now, before we do that, let's move sine of x. We can add sine x to the other side of the equation. And now when we square it, we just have to square the individual terms rather than trying to FOIL this out and creating more square roots. All right, so we add sine x to the other side, and now we can square both sides of the equation. Well, squaring the left-hand side gets rid of that plus or minus square root, and squaring the right-hand side gives us sine squared x. We have 1 plus cosine x over 2 is equal to sine squared x. We can get rid of the fraction by multiplying both sides of the equation by 2. 1 plus the cosine of x is equal to 2 sine squared x. And this looks much better now. The only issue is here I've got a sine of x, and on the left-hand side I've got a cosine of x. Well, since we can't factor out any greatest common factors, we might want to think about using identities to rewrite our trig function in terms of our trig equation in terms of a single trigonometric function. Using a Pythagorean identity, we can replace sine squared x with 1 minus cosine squared x. That gives me 1 plus cosine x is equal to 2 times the quantity 1 minus cosine squared x. If I distribute that 2 through, I get 1 plus cosine x is equal to 2 minus 2 cosine squared x. And this gives us a quadratic. Notice the squared cosine and the first power of cosine. Well, how do we solve quadratics? We set the equation equal to 0 and we factor. So let's bring everything over to the left-hand side of the equation. Bringing everything over to the left-hand side, that gives us 2 cosine squared x plus cosine x minus 1 is equal to 0. And now this is factorable. Quadratics, we can factor them into a binomial times a binomial. This one factors into 2 cosine x minus 1 times cosine x plus 1 is equal to 0. And now we can use the zero product property and set each factor equal to 0 and isolate the trig function. Doing so gives us cosine of x is equal to 1/2, and cosine of x is equal to -1. Now that we have our trig functions isolated, we can go to our unit circle to determine our solutions. Okay, what angles have a cosine value of 1/2? Well, cosine corresponds to the x-coordinate. My two angles that have an x-coordinate of 1/2 are going to be pi over 3 and 5 pi over 3. And which angle has an x-coordinate or a cosine value of -1? Well, that is going to be the angle pi. And because we're only looking for solutions between 0 and 2 pi, we don't have to tack anything onto those guys. We've got pi over 3, 5 pi over 3, and pi. You might notice I have not yet circled these as our final answer. The reason being, Because we squared both sides of the equation, we must check for extraneous solutions. We must make sure that each one of these that we found is a solution to the original equation. So let's test it out. Let's plug each one of these quantities into the original equation. If I plug in pi over 3 for x, well, pi over 3 divided by 2, that's pi over 6. So we're looking at the cosine of pi over 6 minus the sine of pi over 3. And we want that to equal 0. Well, the cosine of pi over 6. Here's pi over 6. Cosine is root 3 over 2. The sine of pi over 3, that's root 3 over 2. We get root 3 over 2 minus root 3 over 2, which does indeed equal 0. Okay, pi over 3 checks out. Then we can test 5 pi over 3. Well, if I plug in 5 pi over 3 for x, that gives me the cosine of 5 pi over 3 divided by 2. That would be 5 pi over 6 minus the sine of 5 pi over 3. And we want that to equal 0 as well. Well, cosine of 5 pi over 6. Here's 5 pi over 6. The cosine is negative root 3 over 2 minus the sine of 5 pi over 3. Here's 5 pi over 3. The sine of 5 pi over 3 is a negative root 3 over 2. I've got a negative root 3 over 2 minus a negative root 3 over 2. We add those together and we get 0, right? Subtracting a negative turns into addition. 5 pi over 3 also checks out. And finally, I need to double check my solution of pi. Plugging in pi for x into the original gives me the cosine of pi over 2 minus the sine of pi is equal to 0. Well, the cosine of pi over 2, that's going to be 0, minus the sine of pi, that's 0. 0 minus 0 equals 0. So we tested each one of them, and in this particular case, all of our solutions that we found are going to be solutions to our original equation. We had no extraneous answers. All right, and so there we have an example of using our half angle identities to solve a trig equation.